Hi everyone, and welcome to another mini chemistry lesson. Today I'm going to focus on a concept from organic chemistry, and it's going to be about Sp3 hybridization. I'll talk about Sp2 and Sp hybridizations in another video, but for today I just want to focus on Sp3. So a lot of times in OChem, you are asked to identify the hybridization of an atom. Usually it's a carbon atom just because we use a lot of carbons in organic chemistry. And a lot of you might look at this molecule on the right, that CH4, and you might identify right away that that carbon is Sp3 hybridized. Right? But I really want to talk about what that means. So it's easy to memorize things like, okay, that's a single bonded carbon, it's Sp3. It's easy to memorize that, but I think understanding what's really happening is imperative to understanding more complex concepts in organic chemistry. So let's talk a little bit about what it means for something to be Sp3 hybridized. And I'm going to start by going a little bit back in time to Gen Chem 1. Because all those concepts that you learned are still relevant in organic chemistry, especially this one. So on the left, you can see that I have drawn out the electron configuration for carbon as well as a potential energy diagram to show you how those orbitals are increasing in energy. So we know that carbon has a total of 6 electrons. 4 of those electrons are going to be valence, as we can see that our level 2 electrons contain 4 in total. And they're right here. These are our 4 valence electrons. And the electrons are distributed as we have 2 in our 1s subshell. We have 2 in our 2s subshell. So again, we know that the s subshell has 1 orbital, and it contains a max of 2 electrons, while the p subshell has 3 orbitals, max of 6 electrons, because each orbital can fit 2. So we see that the 1s is full, the 2s is full, and then when we get to the 2p, we want to distribute the electrons one at a time always. And so in our 2p, we have 1 electron in 2 of the orbitals, and then that third one is empty. So this is ground state electron configuration of carbon. However, we can see just from this potential energy diagram that these carbons over here, these electrons, I should say, over here are the ones that are available to bond. But again, we know that carbon bonds 4 times. So what I want to talk about is what is happening when carbon is bonded to 4 other atoms. So in this case, that carbon is going to be single bonded to 4 hydrogens to form that methane molecule. And carbon in this molecule is Sp3 hybridized. So what's actually happening here is our s subshell, our s orbital in our 2s subshell, is going to join with the 3 p orbitals in the 2p subshell, and they're going to meet at an energy level in between the 2 of them. So they are going to combine, and they're going to meet right here in an energy in between the S and the P. And S and P, they're quite close in energy already, so it's very beneficial for them to join together to be at that same energy level, because in a molecule, if all of those orbitals, those bonding orbitals, are at the same energy level, it's a very comfortable configuration for that molecule to be in. So a lot of times when things happen in chemistry, you're like, why is that happening? The answer is usually because it's going to increase stability. And so in this case, what's going to happen is that these 4 electrons are going to distribute in those hybridized orbitals. Okay, so that's our Sp3 hybridized orbital level. And again, I'm going to write this out another time down here. So when we have Sp3 hybridization, that's telling us that all 4 of these orbitals are hybridizing to create 4 Sp3 orbitals. And what that means is that we're going to have 25% S character, and we're going to have 75% P character. So we know that an s orbital is spherical, and a p orbital has like this dumbbell shape, and of course there's 3 of them across the xyz axes. But our sp3 hybridized orbital is going to be a combination of the 2 of those, and we're going to end up, since we have 75% p character, it's going to still resemble the p a little bit more than the s, but we're going to end up with a orbital that's still dumbbell shaped but slightly rounder. So it's literally going to just combine those shapes of those 2 orbitals. And we end up with 4 sp3 hybridized orbitals. Now, if we take a look at the molecule, what that's going to show us is that, oops, I didn't mean to erase that. Okay. What it's going to show us is that we have those sp3 orbitals surrounding that carbon, and we have s orbitals on the hydrogens. So in order to create those single bonds, and again, every single one of those single bonds is a sigma bond. So the sigma bonds within this molecule are resulting due to the sp3s overlap. Okay, so that sp3 on the carbon is overlapping with the s on the hydrogen, forming that bond between those electrons. So that's what it means for a molecule to have sp3 hybridization, or I should say for the carbon in that molecule to have sp3 hybridization. Now, just as a little preview for sp2 and sp, if you have something that's sp2 hybridized, for example, okay, that's telling us that we are hybridizing these 3 orbitals, leaving an available p orbital, right? So that's giving us about 33% s character, 67% p character. Okay, so we have a little bit more s character here. I know that's not exact, but that available p orbital is very important, because if we have something that's sp2 hybridized, that means that we have a double bond. And in order for a double bond to happen, we need to be able to create a pi bond, which is only possible with a p orbital. So that's a little preview for the next video, but hopefully this helped you understand what it means for something to be sp3 hybridized. Thanks, everyone. Feel free to ask questions in the comments. I will respond to them, and I'll see you at the next video.